So we got up to this equation just here. Now recall that when we were last looking at this equation from way back here, here it is, z double dash is this thing. So we're just going to transcribe that now down to here. So we've got minus k on r squared e to the I theta equals this term here. So d2r well, we can cancel this with this, and we've got a real term on this side. That means that this imaginary term in here must be 0. So that gives us r d2 theta by dt squared plus 2 dr dt times d theta dt is 0. If we multiply throughout by r, we end up with this. And that is easy enough to see as the derivative with respect to time t of r squared d theta dt. Let's just check that. Using the product rule, the derivative of this thing here is 2r dr dt times d theta dt plus this thing times the derivative of that, which is this term. Now that equation there leads to a rather interesting result, namely that r squared d theta dt is a constant. So we'll call that constant alpha. And we'll just put a box around this. This is a rather interesting result because it's related directly to the angular momentum of the body of mass m. It's always fixed, always constant. Now the other term that we need, we'll call that one there 1 for the moment, is this one up here. This is real and it's equal to k squared minus k squared on r squared. So what we have from there is the term d2r by dt squared minus, we better write this in, it's r d theta dt squared is minus k on r squared. And if we use this d theta dt here and replace it with alpha on r squared in there, we get that d2r by dt squared minus r times alpha on r squared squared is minus k on r squared. And now we've just got expression here involving r's and t's. And so we're making some progress. We'll just simplify this a little bit. d2r by dt squared minus alpha squared on r cubed equals minus k on r squared. And we'll call that one equation 2. Now this equation 2 looks as though it's probably not soluble, but it is. And the way we do it is let S be equal to 1 on R. And think of r as a function of theta. So that means that r is 1 on s, of course, and we now need to look at the differential operators. So the first, because we need to go back to there and replace that with something. So we'll look first up at d dt. d dt is d, what will we write here? We'll write that as d theta dt times d d theta. And d theta dt, we saw a moment ago from up here, is alpha on r squared. So we'll replace that here, alpha on r squared d theta. So that brings us to dr by dt. The differential operator d dt acting on r gives us alpha on r squared dr d theta. Now, where does that take us? Well, if we go back up to here and differentiate that thing with respect to theta, we get dr by d theta is minus 1 over s squared ds by d theta. So going back to here, we've got alpha on r squared times dr by d theta, which is that. And that's minus r squared times ds d theta. So we end up with minus alpha ds d theta. So we're making some progress. Next step. So we want to go now into here and we want to work out d2 r by dt squared, and that's equal to d dt of dr dt, which is d dt of minus alpha ds d theta, and that is equal to minus alpha times d d theta of ds d theta times d theta dt, and that is minus alpha d2s by d theta squared times alpha on r squared. So we end up with minus alpha squared s squared d2s by d theta squared. And we're almost there, because we can now substitute those back into the equation. So we're going to substitute this expression here up into equation 2. So equation 2 now becomes, so 2 becomes d2r by dt squared minus alpha on alpha squared, actually on r cubed, equal to minus alpha squared s squared d2s by d theta squared minus alpha squared s cubed equal to minus ks squared. And if we divide throughout by s squared and alpha minus alpha squared, we end up with d2s by d theta squared plus s equals k on alpha squared. And as we saw in the preliminaries, this means that s, which as we know is 1 on r, s is of the form a cos theta plus phi plus k over alpha squared. So it's looking very good. If we rearrange that, can we do that in one step? Alpha squared on k, and oops, on its bottom we're going to have 1 plus, we're going to have there a alpha squared on k times the cos of theta plus phi. And of course this looks very familiar. This is alpha squared on k, and we've got 1 plus epsilon cos theta plus phi, where the epsilon is a alpha squared on k, and that's the eccentricity of the conic. So what we've really demonstrated here is that any bodies that move under the inverse square law invariably follow a path which is a conic section. If the E lies between 0 and 1, you get an ellipse. If the E is exactly 0, on the bottom you just get 1, and on the top you've got a constant, so R is constant, that's a circle. If E is greater than 1, you've got a hyperbola, and if you've got E exactly equal to 1, you've got a parabola. So there it is, the final word on the motion of bodies under the action of Newton's inverse square law of gravitation.